Actually, we have been discussing oblique incidence at plane dielectric boundary, and we have discussed perpendicular polarization. That means the electric field vector is perpendicular to the plane of incidence. And here we are going to discuss parallel polarization. That is, the electric field vector is parallel to the plane of incidence. This is the plane of incidence where the incident ray, reflected ray, and transmitted ray lies. Okay, and to start this derivation, this is the incident wave. The direction of propagation I have represented here as Ni, that is the unit vector in the direction of propagation, and Nr is the unit vector of direction of propagation of reflected wave, and this is Nt is direction of propagation of transmitted wave. And here the magnetic field, the direction of the magnetic field is out of the plane, and here it's into the plane, here it's out of the plane. And here we have represented the direction of electric field Ei. Okay, and here this is the reflected electric field vector Er, and this is the transmitted electric field vector Et, and the incident angle is theta I, the reflected angle is theta R, and transmitted angle is theta T. Okay, so to begin this derivation, we need some basic directions, basic things, that is unit vector in the direction of propagation, as well as unit vector of electric field, the direction of electric field, the direction of electric field, the direction of incident electric field, the direction of reflected electric field, as well as the direction of transmitted electric field. So this is the direction of incident direction of propagation of the incident wave. That is, this angle is theta I, so this angle is also theta I. So we can write this unit vector as the cos theta I is the z component. This is z direction. So cos theta I is z component. We know we can write this. This is the unit vector Ni. This is the unit vector Ni, and this is one component, that is z component, and this is another component, that is x component, because this is the x direction and this is in z direction. So we got two components, that is this, if this angle is theta I, this angle is theta I, this component is cos theta I into z cap direction, cos theta I into z cap, and this component is in sin theta I into x cap. Okay, so that I have written here, Ni cap is equal to cos theta into z cap plus sin theta into x cap. That is the direction of propagation of the incident wave. Okay, and then in the next step we need to find out the direction of electric field vector. Okay, this is the electric field vector. So electric field vector in components we can write Ei is the magnitude, Ei. This angle is theta I. Okay, this angle is theta I, and electric field vector and direction of propagation are perpendicular to each other, and this is 90 degrees. So this is 90 degree, this is theta I. So this total angle is 180 degree, and we will get this angle is 180 minus 90 plus theta I. 180 minus 90 plus theta I, that is 90 minus theta I. Okay, 180 plus 90, 180 minus 90 minus theta I is equal to 90 plus theta I, 90 minus theta I, will get 90 minus theta I. Okay, so the electric field vector can be written as Ei is equal to Ei cos 90 minus theta I in minus z direction. Okay, this component is in this direction, so in minus z direction plus Ei sin 90 minus theta I in x direction. Okay, sin 90 minus theta I in x direction. This can be divided into two components, x component as well as z component. Okay, so Ei n cap Ei. This is I can I can write this electric field vector as EI into the direction of electric field vector, the unit vector. Okay, this vector is EI, the magnitude into the direction. The direction is NEI cap. Okay, I have represented here as that direction as NEI cap. Okay, so that is equal to right side EI sin theta, cos 90 minus theta I is sin theta I into minus z cap in the direction of minus z cap plus EI cos theta I in the direction x cap. Okay, so this EI will get cancelled because each term contains one EI on both sides of this equation. Both sides of this equation. So n cap EI we will get as n cap EI is equal to cos theta I x cap minus sin theta I z cap. Okay, and here this is n cap ET. It's in the similar manner we will get the direction of electric field, the direction of the transmitted electric field as NET is equal to cos theta t x cap minus sin theta t z cap. Okay, as well as n cap ER, the direction of reflected electric field, and then then the direction of propagation of the transmitted wave. Direction of propagation of the transmitted wave is NT. Okay, this is NT. NT is equal to cos theta t. Okay, this angle is also theta t. So cos theta t in z direction plus sin theta t in plus sin theta t. This is the x component plus sin theta t in x direction. Okay, as well as this is the direction of reflected wave. N r cap is equal to cos theta r minus z cap plus sin theta r into x cap. Okay. Next is the direction, the wave vector beta 1. Okay, wave vector beta 1 can be represented as beta 1 into Ni. Okay, here the direction of propagation is Ni, and here for reflected wave the direction of propagation will switch into Nr, and here the direction of propagation will switch into here this is beta 2 into Nt. Okay, so this is beta 1 Ni cap, and our position vector is r cap. Position vector r is equal to xx cap plus yy cap plus zz cap. Okay, and let us find out beta 1 dot r. Beta 1 dot r is beta 1, the direction Ni is cos theta I z cap plus sin theta I x cap. Okay, dot xx cap. The position vector r is xx cap plus yy cap plus z cap, and that is equal to beta 1 into, here we will get, if we do the dot product, then x sin theta I plus z cos theta I. Okay. Okay. So we can find out electric field phasor EI as function of x and z is equal to EI0 is the amplitude. So we can find out the electric field phasor as EI0, the amplitude into e raised to minus j beta 1 dot r into the direction, with the direction. Okay, so the direction we have found earlier, that is x cap cos theta. The direction of electric field is x cap cos theta minus z cap sin theta I into the amplitude EI0 into e raised to minus j beta 1 dot r. Also we have found minus j beta 1 x sin theta I plus z cos theta I. Okay, and this is the magnetic field is in the direction of y cap. Okay, this is z cap, this is x cap, and this is y cap, perpendicular to both z and x axis. Okay, so the direction of magnetic field is in y cap, and this we will get EI0 by eta 1. Okay, that is n cap Ni cap cross EI I cap cross EI divided by eta 1 is the magnetic field. So in that way we can find out this is this as y cap EI0 divided by eta 1, EI0 divided by eta 1 e raised to minus j beta 1 x sin theta I plus z cos theta I. Okay, z cos theta I, and as well as the reflected electric field ER of xz is ER0 is the amplitude, and this is the direction e raised to minus j beta 1 dot r. Okay, beta 1 dot r. There the direction of beta 1 is this one, nr. So we found the reflected electric field. This is the e raised to minus j beta 1 x sin theta minus z cos theta r. Okay, as well as the reflected magnetic field HRX as a function of x and z is minus y cap ER0. If you use this equation in NR cross ER divided by eta 1, we will get this as minus y cap ER0 over eta 1 e raised to minus j beta 1 x sin theta r minus z cos theta r. Okay, as well as we will get E reflected, sorry, this is transmitted, E transmitted and H transmitted in this manner. Okay. Let us give the equation number. This is equation 1, and this is equation 2, this is equation 3, HR is equation 4, this is equation 5, and this is equation 6. Okay. So if we apply boundary conditions, boundary condition is tangential components of electric and magnetic field are continuous. Okay, at z is equal to 0, the tangential components of electric field and magnetic field are continuous. That means for electric field, EI parallel of x0 plus ER parallel of x0 is equal to ET parallel x0. Okay, so we can find out put for equations 1 to 6 as z is equal to 0, and we need to consider only the parallel component, because only the parallel component belongs to x-axis or y-axis. Okay, so this is the parallel components: EI0 cos theta e raised to minus j beta 1 x sin theta plus ER0 cos theta r, etc. Okay, for magnetic field, the parallel components are continuous. So we will get EI0 by eta 1 e raised to minus j beta 1 x sin theta, etc. Okay. These equations are to be satisfied for all x when beta 1 x sin theta I is equal to beta 1 x sin theta r is equal to beta 2 x sin theta t. Okay, so if beta 1 x is equal to beta 1 x sin theta is equal to beta 1 x sin theta r is equal to beta 2 x sin theta t, this equation will lead to EI0 cos theta I plus ER0 cos theta r is equal to ET0 cos theta t. Or this implies EI0 plus ER0 into cos theta r is equal to ET0 cos theta t. Okay, as well as for magnetic field, this equation, because of this equation will lead to EI0 divided by eta 1 minus ER0 divided by eta 1 is equal to ET0 divided by eta 2. Okay, so this implies EI0 minus ER0 divided by eta 1 is equal to ET0 divided by eta 2. Okay, this equation 9, and this equation 10. Okay, here we know by Snell's law theta is equal to theta r, so we can write this as theta I itself. So in that way we can write this as we can take this cos theta I outside. Okay, so I had a mistake, I just correct it. EI0 plus ER0 cos theta I is equal to, okay, and then from this equation 10 we will get ET0 is equal to eta 2 by eta 1 into EI0 minus ER0. If we substitute that value in equation 9, we will get, for 9 ET0 is there, so if we substitute that value in equation 9, we will get EI0 plus ER0 cos theta I is equal to eta 2 by eta 1 EI0 minus ER0 cos theta t. Okay, so if we expand this term, we will get eta 1 ei0 cos theta I minus etc. Okay, and finally we will reach gamma parallel, that is reflection coefficient for parallel polarization is equal to ER0 divided by EI0 is equal to eta 2 cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. Okay. In the similar manner, in the similar way, we can find out the transmission coefficient in top parallel also. Okay, we need to substitute ER0. We need to find out ER0 in terms of ET0 and EI0 from this equation 10, and we need to substitute equation 9. We will get another equation. We will get another equation for top parallel, that is ET0 divided by EI0 is equal to, I'm not doing it, 2 eta 2 cos theta I over eta 2 cos theta t plus eta 1 cos theta I. Okay, eta 1 cos theta is the reflection, this is the transmission coefficient. Okay, and this is the reflection coefficient, and we can write a relation. We can write a relation here, relation of reflection coefficient with transmission coefficient. That is, if we do 1 plus gamma parallel, we will get tau parallel into cos theta t over cos theta I. Okay, cos theta t over cos theta I. If we do 1 plus this term, we will get tau parallel into cos theta over cos theta I. Okay. So for perpendicular polarization, this relation was 1 plus gamma perpendicular is equal to tau perpendicular. But here there is a difference. 1 plus gamma perpendicular is equal to gamma parallel is equal to tau parallel into cos theta t over cos theta I. Okay. And if median 2 is a perfect conductor, then eta 2 is equal to 0. Okay. If eta 2 is equal to 0, then we will get gamma parallel is equal to, if eta 2 is equal to 0, gamma parallel is equal to okay, this is equal to 0, this term will get cancelled, this term will be equal to 0, so we will get eta 1 cos theta I minus eta 1 cos theta I over plus eta 1 cos theta I, we will get that as minus 1. Okay, and here tau parallel, the transmission coefficient is equal to, if eta 2 is equal to 0, transmission coefficient is equal to 0. Okay, transmission coefficient is equal to 0. And if we plot the mode gamma perpendicular square and mode gamma parallel square versus the angle theta I, then the square of the mode gamma perpendicular square always greater than square of the mode of gamma parallel. Okay, that means when an unpolarized wave strikes a plane dielectric interface, the reflected wave will contain more power in the component. The reflected wave will contain more power in the component with a perpendicular polarization than with parallel polarization. That means for perpendicular polarization means the electric field is perpendicular to the plane of incidence, and the parallel polarization means electric field in the lies in the plane of incidence. So one of the applications of this one is, actually much of the light received by our eye has been reflected from the surface of the earth. Okay, so if we use Polaroids, then we can filter out the perpendicular components of electric field, and by that we can avoid the glare. This is the equation for gamma parallel, and gamma parallel is equal to 0 when eta 2 cos theta t is equal to eta 1 cos theta I. Okay, eta 2 cos theta is equal to eta 1 cos theta I. At that time, gamma parallel is equal to 0. Let us take this angle as theta BL. Okay, it's known as Brewster's angle. We'll tell it later. And now let me take it as theta is equal to theta B parallel. And this equation becomes eta 2 into, we can write cos theta t as under root 1 minus sin square theta t is equal to eta 1 into under root 1 minus 1 minus sine square theta I. Okay, theta I is equal to, I have taken theta I is equal to theta B parallel. So I can write in this way. Okay, this is the equation X. And we know by Snell's law, sin theta t over sin theta I is equal to n1 by n2. That implies sin theta t is equal to n1 by n2 into sin theta b parallel. Okay, that is sin theta I. Theta is sin theta b parallel. Okay, and so we need to substitute this value in this equation. We will get eta 2 is equal to 1 minus n1 square divided by n2 square. This is not eta. Okay, n1 square by n2 square sin square theta b parallel is equal to eta 1 into 1 minus under root 1 minus sin square theta b parallel. Okay, so this RHS is, I have taken here as LHS. Just flip it. 1 minus sin square theta b parallel is equal to eta 2 square divided by eta 1 square into 1 minus n1 square n1 square by n2 square into sin square theta b parallel. Okay, and that is equal to, if I expand this, I will get this stuff, and then I manipulate this as 1 minus eta 2 square by eta 1 square. I have taken into LHS. 1 minus eta 2 square by eta 1 square is equal to 1 minus eta 2 square by eta 1 square into n1 square by n2 square into sin square theta bl. Okay, and n1 square by n1 square by n2 square is equal to, we know, mu 1 epsilon 1 divided by mu 2 epsilon 2, and eta 1 square divided by eta 1 square is mu 1 by epsilon 1, and eta 2 square is equal to mu 2 by epsilon 2. Okay, so we need to substitute these values in this equation. I'll get 1 minus mu 2 by epsilon 2 over mu 1 by epsilon 1 is equal to 1 minus epsilon 1 square divided by epsilon 2 square into sin square theta b parallel. Okay, so from this equation we will get sin square theta b parallel is equal to 1 minus mu 2 epsilon 1 by mu 1 epsilon 2 whole divided by 1 minus epsilon 1 square divided by epsilon 2 square. Okay, and theta b parallel is known as Brewster's angle for parallel polarization. Okay, at this particular angle, this is the angle of incidence. If this is the angle of incidence, where eta 2 cos theta t is equal to eta 1 cos theta I, then we will get the gamma parallel reflection coefficient is equal to 0. Okay, that means in the reflected wave there is no parallel component of electric field. Okay, that means the polarization happens when the polarization happens in reflection. Okay, if mu 1 is equal to mu 2, that means the permeabilities of both of the medium are equal. Then sin theta bl is equal to, in this equation, if mu 1 is equal to mu 2, we will get sin theta bl is equal to 1 minus 1 divided by under root 1 plus epsilon by epsilon 2. Okay, this is 1 minus epsilon by epsilon 1 square divided by epsilon 2 square, and this we can this can be written as a plus b into a minus b, because this is in the form of a square minus b square, so we can write it as a plus b into a minus b. That means 1 minus epsilon 1 square epsilon 1 divided by epsilon 2 into 1 plus epsilon 1 divided by epsilon 2, and this terms will get cancelled, and the remaining term is 1 over 1 over under root 1 plus epsilon 1 by epsilon 2. Okay, from this equation we will get 1 plus epsilon 1 by epsilon 2 is equal to 1 by sin square theta b parallel. So epsilon 1 by epsilon 2 is equal to, we will get this in this form, and epsilon 2 over epsilon 1 is equal to tan square theta b parallel. That implies tan theta b parallel is equal to under root epsilon 2 by epsilon 1. Okay, and theta b parallel is equal to tan inverse under root epsilon 2 by epsilon 1, and that is equal to tan inverse n2 divided by n1 when mu 1 is equal to mu 2. Okay, so this is Brewster's angle. Okay.